Welcome students. Myself GB Patel, lecturer in Mechanical Department, VPMP Polytechnic. The subject is Thermodynamics, subject code 3331902. Today we are going to discuss the Brayton cycle. The objective of this video is to derive the air standard efficiency of the Brayton cycle. So let us derive the air standard efficiency of the Brayton cycle. You can see here Brayton cycle on the PV and TS diagram. There are four processes of this cycle. Processes 1 to 2 is reversible isentropic process. You can see here on the TS diagram as well as on the PV diagram. Process 1 to 2 is a reversible isentropic process. Reversible isentropic process means adiabatic process, and 1 to 2 is also a compression process. So compression work is done on the cycle. So again 1 to 2 is a reversible isentropic and compression process, that means reversible adiabatic compression process, and WC compression work is done on the cycle. 2 to 3 isobaric process, reversible isobaric process, that is why you can see here P2 is equal to P3. 2 to 3 is a isobaric. Isobaric means pressure constant, and pressure constant, that is why I can write P2 is equal to P3. Okay, same cycle you can see on the TS diagram. During this process 2 to 3, heat is supplied, that is QS. Process 3 to 4 is reversible isentropic process, and it's a expansion process. Reversible isentropic process means adiabatic process, and expansion process, that is why W expansion, W is delivered by the Brayton cycle. And 4 to 1 is isobaric process, that means pressure constant, so P4 is equal to P1, you can see here. So Brayton cycle consists 4 processes, 2 reversible isobaric processes and 2 reversible adiabatic or isentropic processes. You can also see here there are 2 heat interaction. One is Q supplied during process 2 to 3, which is isobaric process, and another Q rejected, which is during process 4 to 1, and it's again isobaric process. Okay, so W net is equal to W heat interaction, or sigma Q is equal to W net. So W net you can write Q supplied minus Q rejected is equal to WE minus WC. What is WE and WC? W is expansion work and WC is compression work. You can also see there are 2 work interaction in this during this cycle. One is expansion work and another is compression work. So W net is equal to W expansion minus W compression, and for cycle W net is equal to Q net, and that Q net is equal to Q supplied minus Q rejected. Now first we define the pressure ratio. It's a P2 divided by P1 or P3 divided by P4. So what is P2 and P3? P2 is a highest pressure of the cycle and P1 is the lowest pressure of the cycle. So highest pressure divided by lowest pressure of the cycle is pressure ratio. So P2 divided by P1, P2 divided by P1, or you can write P3 divided by P4. Why? Because P3 is equal to P2. 2 to 3 is pressure constant, that is why P2 is equal to P3. And 4 to 1 is again pressure constant, that is why it's a P4 is equal to P1. So Rp is equal to P2 divided by P1 or P3 divided by P4. P2 is P3, P2 is equal to P3 and P1 is equal to P4. You can see on the PV diagram P2 is equal to P3 and P4 is equal to P1. So P2 by P1 is equal to P3 by P4, that is pressure ratio. Okay. Now definition of air standards efficiency is W net divided by heat supplied, QS. So W net is equal to QS minus Q rejected divided by QS. So it's a 1 minus Q rejected by Q supplied. Here Q rejection and Q supplied occurs at isobaric process. You can see here 2 to 3 isobaric process, 4 to 1 isobaric process, heat is supplied, heat is rejected. Okay, you can see on the TS diagram also. 223 is isobaric process, heat is supplied. 421 isobaric process, heat is rejected. So heat interaction during isobaric process can be calculated by mCp delta T. Here we take m is equal to 1 kilogram. So heat interaction Qs is equal to Cp delta T, and Cp delta T process is 223, that is why it's a T3 minus T2. And QR is again Cp delta T. So Cp delta T means T4 minus T1 because Q rejection occurs at process 421 and heat supplied at process 223. So you can see here it's a Cp. QR occurs at 421 process. So it's a Cp T4 minus T1 and Q supplied occurs at 223 process. 223 process. That is why it's a T3 minus T2. So Cp get cancelled. So the equation becomes 1 minus in bracket T4 minus T1 divided by T3 minus T2. Say equation 1. Okay. Now consider process 1 which is reversible isentropic process. This process 1 to 2. This process 1 to 2. It's a reversible isentropic process. Reversible isentropic means adiabatic process. And for adiabatic process, this is the pressure temperature relation. For adiabatic process, this is the pressure temperature relation. Here process is 1 to 2. That is why I write here T1 divided by T2 is equal to P1 divided by P2 raised to gamma minus 1 divided by gamma. This is the pressure temperature relation of adiabatic process. Okay. So take the reciprocal on the both side. So I can write T2 divided by T1 is equal to P2 divided by P1 raised to gamma minus 1 upon gamma. And what is P2 divided by P1? See here, P2 divided by P1 is pressure ratio. So T2 divided by T1 is equal to P2 divided by P1 raised to gamma minus 1 upon gamma. And instead of P2 by P1, I can put RP. So T2 by T1 is equal to Rp raised to gamma minus 1 upon gamma. Say equation number 2. Similarly, process 3 to 4, again reversible isentropic process. See here 3 to 4 on TS diagram 3 to 4. Reversible isentropic process. Reversible isentropic process means adiabatic process. And for adiabatic process, pressure temperature relation can be write in this way. Here process is 1 to 2. That is why I write here T1, T2. Here process is 3 to 4. That's why I have to write T3 divided by T4 is equal to P3 divided by P4 raised to gamma minus 1 upon gamma. And you can see here P3 by P4 is Rp. P3 by P4 is Rp. So T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma. T3 divided by T4 is equal to P3 divided by P4 raised to gamma minus 1 upon gamma. What is P3 divided by P4? Rp. So T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma here. Say equation number 3. Now see the right hand side of equation 3, which is Rp raised to gamma minus 1 upon gamma, and equation 2, right hand side of equation 2, that again Rp raised to gamma minus 1 upon gamma. That what it means? Equation 2 is equal to equation 3. So I can write T2 divided by T1 is equal to T3 divided by T4 is equal to Rp raised to gamma minus 1 upon gamma. Here again you see equation 2, right hand side of equation 2, that is Rp raised to gamma minus 1 upon gamma. Right hand side of equation 3, Rp raised to gamma minus gamma minus 1 upon gamma, both are same. So equation 2 is equal to equation 3. This portion I take here. T3 by T4, T3 by T4, Rp raised to gamma minus 1 upon gamma, Rp raised to gamma minus 1 upon gamma. And this is equation number 2, the portion of equation number 2. This T2 divided by T1 is Rp raised to gamma minus 1 upon gamma. So I put T2 minus T1. Okay. Uh, Consider this two step. Okay. Take this T4 on the left hand side and this T1 on the right hand side. Take this T4 on the left hand side and this T2 on the right. Exchange T2 and T4. Okay. So T4 on the left hand side, T4 divided by T1 and T3 divided by T2. Just exchange T2 and T3. Mathematically it's okay. So equation become T4 divided by T1 is equal to T3 divided by T4. Now add -1 on both side. We can do, mathematically it's correct. So I add -1 on both side. You can see here -1 on both side. So I can write T4 minus T1 divided by T1 is equal to T3 minus T2 divided by T2. Okay. Exchange T1 and T3 minus T2. Exchange this. T1 on right hand side and this T3 minus T2 on left hand side. So I can write T4 minus T1 divided by T3 minus T2 here, and this is T1 divided by T2. And what is T1 divided by T2? See here. T2 divided by T1 is Rp raised to gamma minus 1 upon gamma. T2 divided by T1 is equal to Rp raised to gamma minus 1 upon gamma. Hence, reciprocal of this T1 divided by T2, T1 by T1 divided by T2 is 1 upon Rp raised to gamma minus 1 upon gamma. So it's here 1 upon Rp raised to gamma minus 1 upon gamma. Put this value in equation 1. Uh, the left hand side T4 minus T1, T3 minus T2, that is in equation 1 here, this. So efficiency of Brayton will become 1 minus, instead of this T4 minus T1 divided by T3 minus T2, T4 minus T1 divided by T3 minus T2, the value of this you can put either 1 upon Rp raised to gamma minus 1 upon gamma or T1 divided by T2 as you wish. I put first this. Instead of T4 minus T1 divided by T3 minus T2, I put T1 by T2 here. Equation number 1, you can check this. Instead of this, I can put T1 divided by T2. Okay. So my equation of efficiency become 1 minus T1 divided by T2. I can also write instead of T1 by T2, 1 upon Rp raised to gamma minus 1 upon gamma. So 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. This is my second equation. And third equation, 1 minus T4 by T3. From where it's come? See here. T2 divided by T1 is equal to T3 divided by T4. So reciprocal of T1, take reciprocal on both sides. So I can write T1 divided by T2 is equal to T4 divided by T1. Again see here, T2 divided by T1 is equal to T3 divided by T4. Take reciprocal, so we can write T1 divided by T4 is equal to T4 divided by T3. So instead of T1 divided by T3, you can write T4 divided by T3. So this will become the third equation. So this is the air standard efficiency of the Brayton cycle. This is in the form of pressure ratio. This is in the form of temperature T1 and T2. And this is in the form of temperature T3 and T4. Thank you.